few rules, if you please. Please ensure you have your microphone on mute and video off during the presentations. Otherwise, there can be some unfortunate things that happen. Add your questions to the question pane, please. Please be aware of others that are around, and be respectful and welcoming, and be kind and considerate to everybody, please. Okay, thank you. I would say that you'll find our details on the Nottingham and Derby website. The link is there at the bottom. And if you do join, apparently you get 20% discount. Okay, so that's enough from me. I'd like to welcome and thank Amir for volunteering to, well, present to us this evening, and look forward to his presentation on From Bits to Qubits, and I'm sure it'll be very interesting. Okay, can I hand over to you then, Amir?
Yes, hello, and thank you, everybody. And I'm very pleased to be here to talk about this topic. So let me share my screen first. Shall I stop your sharing? Yes.
Yeah, I'm trying.
Okay. Okay. Is it share? Is it visible?
Yes.
Okay, thank you. Right, so again, welcome everybody. My name is Amir Pourabdollah. I am from Nottingham Trent University. My position here is a senior lecturer, and also I am the course leader for BSc Artificial Intelligence. So I have interest in research about artificial intelligence. At the same time, I have some research background on quantum computing. So it's not a surprise that I'm going to talk about quantum intelligence as a bridge between the two areas. Right, so my plan for today is that I'm going to outline like this, that I start from the introducing of quantum computing and very briefly, and then what are the quantum algorithms, what is the quantum intelligence, and so it's the application of quantum computing in the area of artificial intelligence. And also I want to have a quick introduction about what is the state of the art at the moment, and that will help us to kind of adjust our expectation about the area of quantum computing. So, right. So the term or the word of quantum computing these days is quite very much used here and there in the news, and it looks to be the next kind of big area of computer science. And there are lots of applications, lots of active research areas, research directions about this in different areas of science and technology, and pure science as well, such as in drug discovery, protein design, for finance, for some big problems such as the climate change and climate modeling, for material science. And also for cybersecurity, we have lots of discussions about the breaking of the current securities and need for having some more advanced security measures. The role of quantum computing for AI and machine learning also is quite important. For many areas of logistics, for traffic control, for supply chain, these are also the important areas, and also for energy sector as a big example of kind of sustainable development. And also it has application in pure science such as physics and mathematics and so on. So whenever we see some problems which the classical computer are struggling to find a solution in the kind of reasonable time, there could be a chance for quantum computing to come and do something, but it has lots of if and where and buts that we are going to go to that in a short. Right. Well, sometimes it's good to deliver the final message at the beginning. So that's my message to you. That sorry, so far there is almost no demonstration of a significant advantage of quantum computing. So sorry to disappoint, but it is in the very earliest stages. So whatever we discuss these days about quantum computing is not having so far a kind of real sensible solution for a real world full scale problem. So there are something about proof of concept, about smaller scale problems. Computer scientists develop their algorithms, but the limitation of the hardware still exists. And that's why so far we don't have a full scale real problem that has been solved by the quantum computing. There are something, in the news, but these are kind of abstract problems that, or could be smaller scale problems. So that's something that we need to keep in mind, actually. Right. So let me start from something very fundamental. It's difficult to talk to you about this because I know many of you may know about the fundamentals of quantum computing. Some of you know. So I'm going to make sure that we're now in the same page. So quantum computing can be considered as one of the models of computing. So, from in the history of computing, we had mechanical computers that have been inspired by some kind of mechanical phenomena or physical phenomena, such as the mechanical calculator that we had before. If we look at the physical phenomena of electric charge, then it has led to the current classical digital computers. Also, before we had the concept of analog computers. It still is existing. People may look at the DNA protein and will come up with the ideas of biological computers. Maybe people from optics can come up with the optical computers or molecular computers or fluid dynamics. All of these physical concepts can help us to build some kind of models for computing. And finally, the principles of quantum physics and quantum mechanics has led to the area of quantum computing. So we just get these physical phenomena to build a model on top of it. So the main idea behind about how this can work is that we in the area of quantum physics, we have many kind of counterintuitive, kind of weird or spooky properties, such as parallel worlds. So the idea of parallel worlds can be somehow taken to build some computing models, which works on the idea of parallel computing as well. So that's the idea behind this. And one big difference that it has from any other model of computing is that it is not a deterministic model. It is a probabilistic model. So whatever we get from this is going to be taken as probabilities. So it's not a surprise because all of the quantum mechanics and quantum physics are all about probabilities of the particles being here and there. Right. So some of the weird concepts of quantum physics, you may already heard about this. So we know that at subatomic levels, things are discrete and random. And also the particles can be in different states at the same time. So that's the idea of having a parallel worlds. So you may have heard about the double slit experiment, or again single slit experiment. So all of this can tells us that, okay, there are some phenomena that can happen in parallel worlds. And when we measure one of those properties, actually we have collapsed all of those parallel worlds into a single world. So any attempt to measure any property of a quantum can basically transfer us from the multi-universe to the single universe, and basically that's highlights the role of the observer. So in one of the very kind of fascinating ideas in quantum mechanics is that we as observer has some rules in the physical properties. So when we measure something, we basically collapse it to a single measurement. Otherwise, things are in the superposition. So I talk about superposition. Let me just illustrate it to you quickly. So we talk about many of the subatomic particles, including electrons, photons, even the nucleus, or some other kind of properties of the subatomic particles. Suppose that in the real world, sorry, in the deterministic world, if we give energy or stimulate one of the electrons, it can go to the higher orbits. So we can imagine that the ground state is called state 0, and the stimulated state can be called state 1, or excited state. But in the quantum world, it's not like that. We don't have these two kind of states separate. We could have one single electron existing in two states at the same time. So it doesn't matter, it jumps from here and there. It means that it has a probability to be in any of those orbits at any time. So unless we measure, we don't know what is the actual orbit of that electron. So we call this state as a superposition state. And there is a notation that we call it a Dirac notation with Bra and Ket. So we say that this superposition has some probability of being 0 and some probability of being 1. So those probabilities, we call it alpha and beta. Of course, from the probabilistic principle, we know that basically, or let me correct myself. The absolute value of them squared is actually the probability. So alpha and beta themselves are complex numbers. So those complex numbers, if we basically square them, so they will show the probability of collapsing to 1 and 0. So also there is a notation in quantum or quantum computing is called Bloch sphere. So we have a sphere, and these complex numbers, alpha or beta or whatever, are some vectors on the surface of that sphere. So when the vector is just vertical, so we call it 0 or 1 on the two poles. But in the quantum mechanics, we could have this vector pointing to anywhere on the sphere. So basically, those parameters can give us the probability of collapsing to one of the states. So if we have the z-axis on this side, so whatever is above the z-axis has more probability of collapsing to 1. The one underneath that has more probability of collapsing to 0. But otherwise, we can see that one bit or one bit has only two states here. But if we look at this sphere, if we imagine that the vector is basically representing a qubit for us, so this qubit can point to anywhere. So it can, in theory, on paper, it can represent infinite number of points for us. So that will show us the power of the memory. We can have an analogy here, like having a coin being spinned, although it's not a complete analogy. But we don't know if basically what is the current state of the coin unless we collapse it, unless we hit it, and when it collapses, we can say either it is a head or tail, basically. So the same thing can happen for the qubit. So I just wanted to illustrate the concept of qubit here. Now, if you imagine that we have this idea of qubit, we can think about how the memory can grow based on the idea of having a qubit instead of a bit. So in the classical computing, if we have a bit, it could be either 0 or 1, of course. It could be a coin being on head or tail. Now imagine that if we have n of these bits, then in this case, we can represent 2 power of n possible kind of combinations. But at one time, we could have only one of those 2 power of n states. Going to qubit world, again, if we have a qubit in a superposition state with alpha and beta as complex numbers, then those n qubits can have all of those 2 power of n possible combinations at the same time. Although if we collapse them, we can see only one of those states. But the fact that they can represent all of those 2 power of n states at the same time is quite advantageous. And that is basically the power of a qubit. So some people may imagine that okay, this can give us a very high amount of memory. so exponential growth on the memory, but is not actually used for memory because we have lots of practical issues to take a qubit as a unit of memory here. The main power of having this big number of possibilities is in processing. So we can have parallel processing. That's it, quite the main advantage. If somebody wants to use a qubit as a memory kind of unit and have many qubits for lots of memory, then the practical issues could be that, okay, we can't rely on it because it's not deterministic. Even if you have a very complete, perfect physical environment, still whatever we take from one measurement can be different from the other measurement, because that's the nature of the quantum physics. And also because of that, we can't directly read all of those 2 power of n state at the same time at once. The other practical issues is that we have the concept of decoherence. So bits are stable. We can keep bits for years, for many years, but one qubit can change its states or can be expired maybe in a few seconds or a few minutes. So that's very difficult to keep the state. So that's a problem of decoherence. The other problem is the error correction. So when we measure a number of qubits, we don't know is it actually the right measurements or not. So we have some errors that can happen. And because of this error correction and decoherence, there are some hardware solution to basically avoid this to a kind of partly. So people use multiple physical qubits to represent one logical qubit. So that can also works against the memory growth. Right. Let's talk about the idea of quantum circuits. So because of this kind of idea of block sphere, and that can have a vector pointing to anywhere on the sphere, the idea is that if we can build some hardware, some kind of what we call it a gate, to manipulate the state of that vector, perhaps to change the phase of that, or to mirror it, or rotate it along a certain axis or something, we can think about having some gates in the same sense that we could have gates in the classical computer. So we could have AND or NAND or whatever gates in classical computer. Here we could have something similar to that. So I have a list of those gates here, and each gate basically is represented by a matrix. So if we multiply this matrix by the state of the vector, which is that basically alpha 1 and beta 0 or whatever, we could have a different state, which is a kind of rotated version of that's the same vector. Some of these vectors are basically acting such a knot. Some others could act such a XOR. Some of them are parametric, so we could rotate along or around a certain axis with certain angle. Some of the kind of matrices here are 2 by 2, which works on 1 bit or 1 qubit. Some of them are 4 by 4, which works on 2 qubits, and so on. But the idea of quantum circuit is that how we can basically arrange a number of these gates together to deliver a certain job for us. Sorry. So those circuits usually terminate with a measurement. So something like this. So it's a kind of very example circuit here. So we manipulate with those gates either on 1 qubit or a number of qubits. And then finally, at the end of the circuit, we can have some measurements. So those measurements, if we look at it as a kind of probabilistic, then we have to basically repeat this maybe 100 of times or 500 times or 1,000 times to get a good average about what could be the kind of average result. So a kind of typical result from a circuit could be something like this. So we could have that, okay, the state of 0010 has the highest chance to be measured. So that could basically in somehow give us the result of this circuit and can give us a result of the problem solving. All right. So in the same sense that we could use the classical AND or NAND gates to build the units of calculation such as full adder or half adder. In the same sense, also we can have this qubits arranged with connected with some of those gates in a way that they can deliver the same function here for us. So here we have a quantum full adder. But as you can guess, there is not much advantage of doing the same thing of classical computer here. So we have to do something beyond that. But anyway, because of the nature of the case, we are able to simulate those classical calculations here. But what can give us some kind of advantage and higher level of computing is something which are specific to quantum computer. One of those specific things to quantum computer is called entanglement. So in physics, we know that two particles can be entangled in a way that they are dependent to each other. So by dependency, we mean that, okay, if we measure a state of one of them, we can have some understanding about the result of measurement of the other qubit, even if we haven't measured that yet. An obvious example of this is the spin. So a spin of two electrons in the same orbit has to be one of them up and the other one is down. So if we measure one of the spins to be up, we are sure that the other one should be down. But that's just an example. There are many other possibilities of having entanglement in physics. So this can give us some kind of from the computer science point of view, it can represent some of the correlations between data. So we can represent those correlations in a kind of very, very compact way of entanglement. The good news is that we can just easily implement this entanglement in the quantum circuits. So one of those gates is called a CNOT gate. If we put it somewhere in the circuit, then we can cause two of the qubits to be entangled. And it's quite essential in many of the quantum algorithms. So this example, for example, we have two qubits of a state of complete zero coming to the circuit. One of them is going through a Hadamard gate. So Hadamard gate is the one that gives 50% chance of being 1 and 0. So it's a kind of very balanced superposition. So by this point, by the first point, if we measure, actually we don't measure anything. But if somebody is going to measure, there are one quarter chance to be 0, 0 or 0, 1 or 1, 0 or 1, 1. So that's how we show it. So the two here, if we square it will give us 1/4 possibility of having either of these 4 states. But after the CNOT gate, basically the second one is negated if the first one is 1. After the CNOT gate, we can have only one of those 4 states remaining by the chance of 1/2. So we have a 1/2 chance of being 0, 0, the other half to be 1, 1. So if we measure one of them, we are sure that the other one has the same state. Right. So that is basically mathematical view of it. But if we think about the physical kind of concept, the physical meaning of this, it can also lead us to many other areas such as the quantum communication. So which is beyond our discussion today. Right. So here's the example. So on the right side, this picture is a picture of a small quantum computer we have in the department, which has a very limited number of qubits. But I could have this experiment here. So by arranging or designing gate or the arrangement of gate like this, Hadamard and the CNOT, I could have this measurement. You can see that the 0, 0 state has a probability of something near 1/2, 1, 1 about the same, but we have no case of 0, 1 or 1, 0. If we had this one kind of negated, we could have 0, 1 and 1, 0 to have the highest chance. So in that case, it can represent the XOR function for me. So that's another application of that. You see that things are not perfect. So my probability over a number of shots is still not perfect. Actually, this is a very good number. In reality, we could have something even more deviated from the pure results. Okay, the other kind of property of the quantum mechanics, which can help us to build a more powerful computing model, is the interference. So in the interference, we know that waves can interfere to each other, and they can basically constructively or destructively interfere to amplify some of the phases and to cancel out the other phases which are not in the same value. So because in the superposition things are or the particles can interfere to each other, then we can take this kind of property to amplify some of the expected or some of the interested state of the qubits, as opposed to the one which are going to be cancelled out. So that is basically another very important part of the quantum algorithms, that if we interested to see a specific pattern in the output, suppose we are going to classify or to make a classifier, we are interested to distinguish between two cases, then we do those interference in a way that it amplifies the requested or the highlighted class for us, and cancel out the one which are not going to be highlighted. So the idea is that while the qubits are in superposition, while those coins are neither in head or tails, we can manipulate them on the fly in a way that if we collapse them, it can give us the result that we wanted to be. So that's basically taking the advantage of the qubits actually in the very physical layer to be waves. Right. So from perhaps these three major properties, entanglement, superposition, and interference, we can start to think about some new ways of building the circuit, not only to make the half adder or full adder or do the same thing as classical. We can think basically something new. So we can simulate any classical computation as a kind of universal model, but the quantum advantage is only for a small set of problems. So those properties so far has only shown their advantage in a very specific or a few number of problems. It's not universal in solving any problem. Or it's not universal to show advantage in solving many problems. So far, the main algorithms which are developed in the literature, which are the basic of many problem-solving scenarios, are this list. So we have Grover search. Grover search is a search algorithm in a database, but is not basically good for retrieval information. It is good for finding a specific pattern in a database, or finding one of the records of a database which satisfies a specific rule. So of course, this is not what we normally use in the classical databases. But if we have a scenario in which we have a database where one of the records is our interest, which satisfies a certain rule, the Grover search can give us an advantage. The other one is Shor's factoring, which possibly the most kind of interesting application here. So factoring a number to its prime factors is the essence of decrypting any encrypted message in the current cryptography. So on the right side, I've shown you an example of the Shor algorithm, Shor factoring, just for a 4-bit number. So if our number can fit in 4 bits, the circuit can be used to factorize the number. Quantum annealing is another algorithm which is used for minimizing objective function if the objective function is in a very certain form. Quantum approximate optimization algorithm, QAOA, is another version of the quantum annealing. So quantum annealing itself is done at the physical level without having a specific circuit, but the QAOA is a simulation of that physical transformation in the quantum circuits. Again, can work only on a certain type of the objective function to be minimized. As an example here, that's a Shor algorithm for factorizing a 4-bit number. if we apply it to a number of 15, which can fit in 4 bits. So here is the result when we get it from this small quantum computing the department we have. But the way that we have to interpret this algorithm is quite tricky. So this algorithm is only gives us the period of repeating some of, or a part of the algorithm is reduced to finding the period of repeating some patterns. And that specific part is the one that classical computing is struggle to do that. But the quantum computing can basically show advantage on that specific part. So in that case, we can see that there is a period of 2. This period of 2 can help us to find the factors of 15 to be 3 and 5 in this example. But if you have a big number with larger number of qubits, it's very, very difficult for classical computing to find this period. So that's where it can show the advantage. I can tell you where we can see the real advantage of this in another slide, or when we can see the advantage. Right, so let's switch to the concept of quantum machine learning, which is basically one of the areas of quantum intelligence, when we can use the idea of quantum computing for machine learning. So that's very quite active research, and people try to have different arrangement of the circuits to deliver a specific machine learning task using the quantum computers. So we can say at the moment the current research is to find some quantum counterparts for the classical ML. So people take some classical machine learning such as neural networks, SVM, clustering, PCA, GAN, from different aspects of pre-processing to post-processing of the classical machine learning, and then add a qubit before that to find the quantum version of that. So for example, quantum neural network is a bold example of this. And the main idea of building this kind of arrangement is to formulate a circuit to amplify the probability of a certain output for a given input. So the way that we encode the input is quite, unique to quantum computing. But the way that the system works is that we are going to use those entanglement and interference to increase the probability of having a certain class or certain output at the end of the circuit. So for example, if we apply it to, let's say, neural network, we can have some more compact solution. We could avoid some of those classical issues such as the vanishing gradient. We could have some few parameters and shallower circuit to represent the same, classical machine learning if we do it in quantum computing. And the reason that it can be more compact is all because of, or all thanks to the parallel processing. Some of those complex data patterns, some of the perhaps very hidden non-linear correlation between the data can be discovered by quantum neural network, which couldn't be discovered by the classical one, perhaps. So some data could have some hidden interference to each other that can cancel out each other or amplify the other state that can give us whatever we want as output of the machine learning. And because of this, we have some very problem-specific advantage. Not every classical machine learning can be done better in quantum machine learning. Actually, most of them cannot be done. It's very problem-specific when our data pattern is complex in a certain way. But at least we know that perhaps it can give us a kind of shorter, more compact solution than the others. And the other point is that many of these, or perhaps almost all of these quantum machine learning algorithm has a hybrid structure. A part of that is done in classical ML, and the other part is done in quantum circuit. So the very basic model of doing the classical machine learning is that we start from classical input. We have some data encoding, which is specific to quantum computers. We do the parameterized quantum circuits. So we build a circuit with the parameters which are specific to this problem. And then we try to optimize those parameters. First, we measure the circuit, and then using a classical optimizer, we try to have a feedback loop try the same algorithm with some optimized parameters, something similar to what we have in the quantum neural network and backpropagation. So here I have a circuit here which can represent a kind of quantum neural network for us. One of the main differences is that our inputs are not the qubits. So our inputs main inputs to the circuit are just a number of qubits which are starting from the state of pure zero, and then the data itself is basically showing themselves in the parameters of some rotations. So the rotation is just one example of embedding the data, but in one simple scenario, the data can be used to rotate those qubits. Based on the value of those data, we can rotate the qubits to get the embedded input, and then we have a number of layers similar to the layers of the neural network that have the parameters of which are not the data parameters, but also the parameters of the optimizer. So those parameters can be different layers, and also we use the advantage of the entanglement between them. So with a series of these gates at entanglement, we hope that the system can discover some of those very hidden nonlinear patterns of the data. And then during the backpropagation, after measuring the output, instead of tuning the weights of neural network, here we tune the parameters of those rotations or those gates, which are existing in the hidden layers of the neural network. So that's a very kind of general solution that people do with quantum neural network. As you see, it has a classical part. The classical part is when we are going to feed back the loop and do the backpropagation and rerun the circuit with some optimized parameters. Okay, optimization by itself is a quite distinctive area of quantum computing or research. So the idea is that we are going to find the minimum or maximum or optimal value of an objective function. We have a combination of the different approach here. In pure quantum, when we have just the quantum machines and quantum hardware, we have an algorithm called VQA, variational quantum algorithm, which, as I said, we try to have a quantum circuit with some parameterized gates, and we are going to use that objective function to find the best value of those parameters. Quantum annealing, as I said, by itself is a physical system, which is inspired by the simulated annealing when we have in classical optimization. But it only works for a very certain objective function, which is called QUBO, quadratic unconstrained binary optimization. And the advantage of this is that at the physical level, we have a concept of quantum tunneling, which can help us to escape very efficiently from the local optimums. And as I said, QAOA is the circuit version of the same algorithm, but with some parameters. Basically is a compromised version of that very physical phenomena, which can be done in quantum circuits. We have some hybrid methods. The hybrid methods is basically using both classical and quantum machines to deliver a optimization job. For example, we can use classical machine learning to train, to mitigate errors, to tune parameters of a quantum algorithm. On the other side, also, we could have some quantum algorithm used to tune and speed up a classical algorithm parameters. Again, that is kind of both ways. Apart from these two, also we can have quantum-inspired algorithms, which are completely classical, completely using the classical hardware, or let's say the current hardware. But the algorithm itself is inspired by the concept of the quantum mechanics or quantum computing. We could have some scenarios when we simulate quantum principles by or as a part of a classical algorithm. One example is SQBM by Toshiba, which they use it for industrial scenarios to optimize some objective functions. but they are not using any real quantum hardware. The other area is simulating quantum algorithm on HPC hardware. So we can use platforms with GPUs or with FPGAs or a network of all of these HPC hardware that are being inspired by the algorithms of quantum. So we can simulate those parallelism within FPGA. We could do the same parallelism in network of GPA, and there is active research here to how to use FPGA. Again, in our department we have a FPGA cluster, which we are hoping that can be used to simulate some big quantum algorithms simulated. Right, here's an example of one of my basically previous research to use applications of quantum optimization for fuzzy systems. So in fuzzy system, we have many scenarios that can be very complex mathematically. And one example of that is something in type 2 system when we are going to do defuzzification. So there is no kind of closed form calculation to find the result of this Carnegie-Mendel algorithm, but using an quantum annealing optimizer, I could find some equivalent problem in that is kind of quantum friendly problem that can be solved easily with quantum. And we can see that I've shown in that paper that the same result can be found in the using a quantum annealer. The other example is that the one that one of our PhD students, Amir, I think Amir himself is here, is working on it, which is using the idea of QAOA, the quantum annealing circuit model, to tackle some of the real world optimization problems, such as in the energy sector. So you can see that what he is doing is that he has layers of parameterized quantum gates back to back. So on each one, the parameters, for example, gamma or beta, can be optimized in a back propagation loop. So finally, it can deliver the optimization of the objective function, which are specific to that energy sector problem. Okay, let me have the rest of the slide on the state of the art. So the overview of the current technologies is quite important to know. So the first thing is the technologies which are used to implement the qubits. So we can have different physical implementation of the qubits. Each one of them has advantage and disadvantage. So one of the very common one these days is superconducting qubits, which needs a very specific mini Kelvin temperature. Very powerful refrigerators has to be used to make the system stable. It's very noise sensitive, but people trying to mitigate those sensitivities. IBM, Google, Rigetti, Oxford Quantum Circuits, all of them are using this technology. The other technology is trapped ions. It doesn't need that much of temperature to be cooled down, but it has some complex laser control. So the laser is used to basically deliver the job of those quantum gates, and also to measure. So very kind of delicate kind of technology needed to control those lasers. Companies like Honeywell, IonQ, and Quantinuum are using this. Photonic qubits are using by other companies. Spin qubits by Intel, which is using a technology of semiconductor. Still needs a low temperature, but not as low as the first one. Microsoft recently experimentally shown a technology called topological qubits. It still needs a very low temperature, but they claim that it can be scaled up very quickly and can mitigate the error much easier. And also there is another technology, NMR, which is used for very small scale quantum computers, such as the one we have in the department. It has a very limited scalability, and also some kind of issues, not issues, I mean some principles of quantum computing has been compromised here. So that the measurement is not actually the physical measurements. Right. So SpinQ is a company, is a Chinese company which does this in ML. One term that we hear a lot these days about the quantum technology is called NISQ era. So we are now in noisy intermediate scale quantum. We don't know how many years it's going to last. Maybe by 5-10 years at least it can last. So in this era, we can have only up to a few hundreds of qubits. We still have noise, decoherence, all because of the hardware issues. And at the moment, we have some overheads, such as 100 to 1,000 of physical qubits per logical qubit in order to mitigate those errors. It's still experimental, it's still a smaller scale, and it still is using for proof of concept. So still we are in NISQ era, same as the one that we had for classical computers many years ago. Then we had very small scale real classical computers. Let's also have a very kind of a short review about the current hardware or current platforms that are basically run by the big names around the world. So IBM is one of the pioneers in this area. So their latest hardware is called Heron. It came December 2023, which has 156 qubits. Their future plan is to make this one modular, so it can be scaled up in a very innovative way to thousands of qubits. Google, as we heard in the news recently, and last year, I mean, they introduced the Willow, Google Willow, with 105 qubits, and they say that it can be scaled up in a kind of efficient way. In 2023, Quantinuum H21 presented their 66 qubit hardware. D-Wave is a pioneer in the quantum annealing, and they do something such as 5,000 qubits, but these 5,000 qubits are not very much comparable to others because these are the annealer machines, and the annealer machines have their own limitations. So one of the limitations is that we can't basically use any of those, any pair of those 5,000 qubits together. So they has to be physically next to each other or in very close proximity to each other. So, but the scale is quite impressive at the moment, 5,000 qubits with its own limitations. And also they recently claimed that they can solve some real industrial problems. Oxford uses a technology called Toshiko Gen 1 with 32 qubits. And also Microsoft, as I said, they introduced a topological qubits. The first product is called Majorana 1, just recently in February 2025 with just 8 qubits, but they have a kind of a very big plan of this to be scaled up, because they claim that these topological qubits are very much scalable and they are very fault tolerant. So they said that they can scale it up to 1 million qubits. We don't know when, but it has a potential to do that. Although I have seen some articles that they have criticized their claim. Also, it's good to know about the platform, the cloud platforms, which at the moment providing the real quantum computing services to public or to industries in different kind of business models. So IBM Quantum, which is basically providing the service over its own hardware, is one of the big players here. Microsoft Azure just intermediates some of the third parties, such as Quantinuum, IonQ, and Rigetti, so people can use their Azure account to access those third-party services. Google Quantum AI, they have their own hardware, so they provide the service over the cloud. And also Amazon Brackets is another part of the AWS, which again intermediates some of the third-party providers, such as the Oxford Quantum Circuits and so on. Right. if you just want to have a very estimated rough ideas about what's going on in the next years, so still we can have those application areas, but we can imagine that, okay, in 5 to 10 years, perhaps we could have, or we can have about something about 500 to 1,000 logical qubits. Of course, we have overhead over that. So it can tackle some of the real world optimization problems, such as the one in energy sectors or in logistics, or maybe in other kind of business areas. In 10 to 15 years, perhaps we could have something about 1,000 to 2,000 logical qubits, which can be used for protein design, for molecular design, for more advanced quantum machine learning, when the machine learning can show its advantage. And in something about 15 to 20 years, we could reach to a limit that can be used for cybersecurity purposes. So RSA 2048 can perhaps be broken by that time, when we have computers with 20,000 logical qubits in place, where we can break this security barrier. Just heard in the news that in 12 of March of 2025, D-Wave, as I said, they demonstrated an advantage in the real-world application simulating complex magnetic materials. They claim that the same problem could take about 1 million years on a GPU cluster, but they could solve it with 20 minutes. So again, that's something newly claimed. So still people are trying to criticize it. Okay, what quantum computing can do or cannot do is quite important to know. The quantum computing is not going to replace our day-to-day job. It's not going to have a quantum phone in the future. It's only useful for a specific problem, as I said. So we have to narrow down our expectation, what problem, what scenario can be done, and when. And many AI problems still require classical computations, and still we have some errors and probabilistic issues due to hardware imperfection that has to be solved. Okay, so that's my final slide. So as a conclusion, first of all, we know that we have a good potential here using some of those physical properties that to build a powerful computing model. It's universal, but only for advantages for a specific computation, a group of computations. It has a potential in AI, in machine learning optimization, but till we go out of the NISQ era, we can't see some real world applications out of that. But still we're trying, as computer scientists, we try to build algorithms for the time that the hardware is ready. Okay, so that's the end of this. Thank you very much. So here is my email. And thanks for your patience. I'm happy to take questions if the time remains. Thank you.
Right. Thanks, Amir. That's great. I'd like to thank you on behalf of everybody for a very interesting talk, and we're looking forward to questions. Bev, I understand you're monitoring those, so
Yes.
put those forward, please.
I couldn't click my microphone button then. So yeah, we've got one question. We've got time for a few. We've got a question: can quantum computers be programmed with languages? Oh, they're all moving, like Java, C++, or Python.
Yes, good question. At the very heart of the quantum computer, no, but there are some libraries that can give us some kind of overlays. So we can have a library in Python, for example, called Qiskit. So we can have those circuit design in the syntax of Python, but the library itself knows how to work with the hardware. So those libraries are also available either in simulated simulated kind of mode, or the real mode, or the hybrid mode. So we just define what is the back end of the computation, and then when it comes to the real kind of circuit implementation, either simulated or uses a real quantum computer. So the answer is yes.
Okay, thank you. And then we've got where's it gone? Question from Mark. So I see a reference to gates. Are these part of the Qubits circuit?
Are these part of what? Are references to gates? Yes,
Yeah.
yes. So the gates, as you said, are the parts of the quantum circuit. Yeah. So when we have these gates, we can build a circuit. We normally start from the basic states, and then we try to basically put it in superposition, and then while they're in superposition, we just apply different gates, and we at the end of the circuit we just measure them and just work on the probabilities which are coming out of a histogram. So that's a very common scenario after that. So yes, these are all parts of the circuits.
Okay. Thank you. That's all the questions in there at the moment. So I think I'm going to take the opportunity to ask you a question, even though I could do so most of the time. So you mentioned there's kind of no real significant application of this in the real world at the moment. What do you think is going to be the most promising big application of this that we might see soonish?
Yes, I think the one which are involving optimization could be the early ones. As I said, we have at the moment some claims from companies such as D-Wave that they have approached some real world problem in the industry. So anything that can be converted to a specific form of optimization can be tackled with them. I think that quantum annealing itself is most promising than the other models because a very kind of clean formulation is behind that. So when we have a more kind of stable qubits, then there's a big chance of tackling optimization problems. And following that, some of the common artificial intelligence problems using that. But we are not going to expect the kind of revolution about the artificial intelligence. Only some of the problems with the AI is struggling to find the best kind of optimizer, or may struggle from very complex networks, could benefit from some kind of quantum intelligence maybe in 5-10 years.
Okay, thank you very much. And I think just one final question in amongst all of the thank yous. People have very much enjoyed it and given them things to think about. And Mark has posted a link to IBM's quantum roadmap for anybody that's interested. So, okay, there's two quick questions, questions come through, but we
does a gate observe a qubit? Yeah, can I read the question?
Yeah.
Does a gate observe a qubit and causes it collapse into a state, or does the whole circuit remains in superposition and is only the final measurement that observes? Well, each individual qubit can be observed, but as you said, when we observe something, then we destroy the whole things. So only one of the states can be measured. But our hope is that before measurement, before we come to the end of the circuit, we have done all of those useful calculations or manipulation over the qubits before we measure them.
Okay, and then I guess last one. Then, can quantum computing manage natural language like Gen AI, or is it capable of dealing with data only?
No, I think Gen AI is an active area here. So people, I've seen many papers that working on the quantum version of Gen AI. Although because of the advancement of the classical Gen AI, still very much ahead of the any other technology. But maybe for some certain Gen AI problems that needs very high parallel computations, could quantum computing be a solution? The other aspect I'm thinking of is that the energy. So the quantum computer may perhaps with some lower level of energy can achieve the same level of intelligence for Gen AI. So it can be better to conserve from the energy point of view.
Excellent. Right, I think that's it then. So thank you very much, Amir, on behalf of everybody. So yeah, if the audience, if you're interested in finding out more, then Amir did post his put his email address at the end. Otherwise, you can contact the branch, and we can put you in touch. So yeah, thanks everybody, and I hope you enjoy the rest of your evening.